So in this module, we'll talk about better initialization strategies. So this is where we are in the story, right? We saw that deep learning has evolved, and at least these are the 4 things which have happened. So yeah, by the way, this slide is incomplete. What are the other things which have happened actually? Which you already said in the beginning. 2 more things which are not technical, but which happened. More data, right? And more compute. But these are not really technical in the sense that, I mean, this just happened. We have large amounts of data. That means more data means what? If you have more data for training, you could have complex networks but not overfit, right? Because you have so much of data, right? And more compute, of course, it speeds up some of these matrix computations which happen. So remember, in a deep neural network, most of the things which you're doing are matrix operations, right? You're taking that's what exactly you did in your backpropagation assignment. You did a lot of matrix vector computations and so on. And with the advent of GPUs, this became very, very fast, right? Orders of magnitude fast. So these 2 which are here is nothing much to talk about that. That's just something we all understand what has happened there. And so now we'll talk about better weight initialization strategies. So let's start with this question, right? We'll take this network and we'll ask this question: what happens if you initialize all the weights to 0? I like it when you all try to visualize it. And okay, so we have to see what happens, right? So let's start with A11, okay, which is W11x1 plus W12x2. So always start small, right? Don't try to see what will happen everywhere. Just start with 1 neuron and see what happens. Take A12, okay. What would A11's value be if all the weights are initialized to 0? 0. And A12 again 0, right? And same for A13, right? So all the neurons in this layer are going to be 0. They'll be 0, okay? So that means they'll all get the same activation. So if the A's are same, the H's are also going to be same. Right? That's obvious, irrespective of what nonlinearity you use. Now what will happen during backpropagation? What will delta W11 be? This, again, I don't know why I do this. Okay, anyways, I'll erase it. Into x1, right? So remember that the gradient is always proportional to the input. And you have somewhere along the lines, along the chain rule, you have this h11 and a11, okay? Just remember that. And what would delta gradient of W21 be? Is that fine? Okay. Now, can you see some things on the left-hand side and make some comments on the gradients? We have seen that A11 is same as A12 and H11 is same as H12. That means these gradients are going to be equal, right? That means the weights started off at the same value. They're going to get the same updates and again remain at the same, a different value but the same, right? They'll of course move from where you started. They'll not be 0 anymore, but they'll all be at the same value, okay? Both the weights will get updated with the same value and they'll remain equal. So, but fine, right? As I keep training, they'll move away from each other, right? This is what I told you when you feed in the first example. Okay, both the weights remain the same. But now if you feed another example and you keep feeding batches, right? There's no dearth of data that you have, then eventually these weights will move away from each other. The updates is the same. Again, the weights are the same. Again, the same situation will hold, right? Again, your W11x1 plus W12x2 is going to be the same as W21x1 plus W22x2, and the same argument repeats. How many of you get this? Okay. So once you initialize the weights to 0, in all subsequent iterations, the weights are going to remain the same. I mean, they will move away from 0, but they will all be equal. Okay. And this symmetry will never break during training. So what actually is happening in terms of the capacity of the network? This is same as tying the weights. So this symmetry will never break during training. So I was asking what's the net effect which is happening. So you have so many weights in your layer, but all of them are moving together, right? So in essence, you don't have the same freedom as you have with n different weights, right? You have in some sense unintentionally tied them because you started off with the same value. Now you're all moving at the same values, right? You're all going to the same value. So you don't really have the amount of freedom that you would actually expect with n different parameters. All of you get this? Okay. And the same is true for W12 and W22 also, which are the weights connected to the second neuron. And this is in fact true for all the weights in layer 2. You can actually mathematically verify it. That means whatever this small analysis that I did here, just go back and do it for all the weights in the network. and you'll see that all of them, if you're going to initialize them to 0, all of them are going to remain equal. Okay, this is known as the symmetry breaking problem. Okay, this is a known problem. This has existed much before 2006 and so on. If you initialize all the weights to 0, you'll have the symmetry breaking problem. Is there anything sacrosanct about 0, or would this happen even if you initialize it to same but non-zero values? And that should have been cleared from the iteration, right? Because after the first iteration, we were at non-zero weights, and after that, the story repeated, right? So even if you initialize it to non-zero weights, the same story is going to repeat. So that means, as long as you initialize all the weights to the same value, you're going to end up with this symmetry breaking problem, okay, which is not good. So what is it that we have learned about initializing weights? Definitely do not initialize all weights to 0. Definitely do not initialize them to the same value. Okay, this is the first thing that we have learned. So we are seeing different ways of not making the light bulb, and then we'll come to a way of making it. Okay, so 0 and equal is no, bad. Yes, some weights will not get updates in that case, right? So then that should be fine. Yeah, so that's the other thing I wanted to make at some point, right? So these 4 things, right? Initialization, optimization, regularization, and activation functions. These are not independent things, right? They're all tied to each other. So as you said, now if you use regularization, then probably you could be a bit careless with the initialization. Even if you had initialized the weights together, dropout would have ensured that some of these weights are not active at a particular training instance. That means they will not get weight updates. That means they will move away from the other weights, right? So this is not that only one of these things can be done, right? You're going to use a combination of these things. But while analyzing them, we'll just look at one of these things, assuming that the others are not being used, right? So we'll assume that we are not using dropout or anything. Is that fine? Okay. Okay. So this, at least this in practice, you are not supposed to initialize the weights to zeros and equal values. That's what we have learned so far. Now for the rest of the, to convince you about some other weight initialization methods, what I'm going to do is, I'm going to take a feed-forward network where you have as input some 1000 points. Each of these points is 500 dimensional, okay? And the input data is drawn from a unit Gaussian. What I mean by that is you have this x11 to x1 500, right, for the data instance 1. So all of these 500 dimensions come from a unit Gaussian. Is that fine? So this comes from a unit Gaussian, this comes from a unit Gaussian, and so on. Okay, that's what I'm going to assume. And the network has 5 layers. Each layer has 500 neurons. The input is 500 neurons. Each of the 5 layers is also 500 neurons. And now we'll run forward propagation. No backward propagation, no loss, nothing, right? I'm not even giving you an objective. This is just some input, and I just want to see what happens up to the last layer. I'm not even bothered about the actual last layer. That means I'm not trying to minimize any cross entropy, squared error loss, anything, okay? So let us try a few initialization strategies. So we realized 0 is not good. We realized equal is not good. So let's try some random initializations, but small weights, okay? And this is my way of randomly initializing with small weights. So my W is a matrix of size fan in into fan out, right, which is n cross n. Okay, the number of weights coming in and out, right? So n cross n. And I'm drawing from a uniform distribution and then multiplying it by 0.01, which ensures that all the weights are very small. Okay, you get the setup? Now with this, I'm going to start with the input and then keep doing these transformations. So I'll do W transpose X plus B, pass it through a sigmoid and do this 5 times because I have 5 deep layers. Okay. Now this is what happens to the activations across the 5 layers. So the first layer, remember that we had drawn from a unit Gaussian, right? So that's what the data, input data looks like. So this is the first layer, which is the input data basically. And then this is what happens across the different layers. So what is actually happening? And this is for the tanh activation function. There is no variance in the output of, so this tells me, so this basically tells me that for all the neurons, what is the average value that I'm getting, right? And I should ideally get some histogram that for some neurons, I'm getting the value -1, for some neurons minus 0.9, 0.8 and so on. But what this is telling me is as I keep progressing across the layers, all the neurons have very similar values and they are all close to 0. This is what actually happens in practice. I've just actually run it and computed the histogram, okay? And if I use sigmoid activation functions, again something similar, all the values tend to be close to the center, which is 0.5, right? So this is 0.5. And although I had started with a nice Gaussian distribution. Okay. Now what will happen during backpropagation? So don't try to think for now that why this happens. I'm just telling you I've actually run the code and this is what happens. Now given that this has happened, what will happen during backpropagation? So if all the activations in a layer are very close to 0, all the gradients are going to be close to 0. That means no gradients are going to flow back. That means which problem are we dealing with? Vanishing gradient problem. So if you initialize your weights to very small values, okay, and this is easy to see in the case of tan h, okay. So for tan h, this is my function, right, and this is 0. Now remember that this is wi summation wi xi. If all my weights are close to 0 or very small values, what is summation wi xi going to be? It's going to lie somewhere here, right? So all these inputs are actually going to be very close to 0. Now if my inputs are going to be close to 0, I know that during backpropagation, at some point, my gradient is proportional to the input that I have given. And when I say input here, I mean layer 1, layer 2, layer 3 and so on, right? How many of you get this so far? Okay. So that means all my inputs are very close to 0. Now my gradients are actually proportional to the input. So all my gradients are also going to be close to 0. That means my gradients are vanishing, right? Because remember that across 5 layers, you'll have these products of gradients, right? All of them are very close to 0. So you'll end up with something very close to 0 raised to 5. How many of you get this? Right? So gradients are going to vanish if you do this very small initialization of the weights, and that is exactly what is happening. So this is the histogram for the gradients, and I see that all my gradients are actually very close to 0. That means no effective training is happening. My weights are not receiving any updates. This is what happens in practice if you initialize your weights to very small values. Okay. Now let's try to do the opposite of this. Very small values did not work, so let me try large values. Right? And for large values, I'll just sample from the uniform distribution. I'll get some numbers between 0 to 1. Now can you guess what will happen? Remember summation wi xi. All your weights are large. So why am I saying that number between 0 to 1 is actually large? It's not by all practical, because this is going to give me, this function is actually going to give me numbers between 0 to 1. Why am I calling them large weights? No, let's just talk about the weights. Assume there is no biases. How many of you get that answer? Remember there are 500 neurons. So if you have 500 small values, that summation is going to be still large, right? If you, all of these are 0.4 or 0.5, which still looks small, but if you have 250 of these, or if you have 500 of these, the resultant sum could be somewhere of the order of 250, right? And that's very large, because if you pass that to a sigmoid neuron, what will happen? Saturation, right? So you get this, why I'm calling these weights as large? Okay. So, and this is actually what happens. So when I have these tan h activations across all the 5 layers, I observe that my neurons saturate. I either get -1 as the output or +1 as the output. And same thing happens if I use sigmoid activations. I either get 0 as the output or I get 1 as the output, right? Neurons saturated means what will happen? Gradients will vanish, right? So even if you initialize the weights to very large values, all your gradients are going to be close to 0 because they're going to vanish, and again you have a problem. So what have we seen so far? 0 is not good, equal is not good, small weights is not good, large weights is not good. Then what do we do? Go home? Okay, so let's see what to do. So let us try to arrive at a more principled way of initializing weights. And this, again, don't shoot the messenger. I'm going to give you a proof under certain assumptions, okay? So just bear with me. I'll just tell you what those assumptions are going to be as we go along. So as I said, right, so I mean, you would argue that in practice these assumptions don't hold true, but at least they give us some insights into what is happening, right? What's the overall idea behind what is being proposed. So let's start with that. So now consider this deep neural network, and I'm just considering the first layer of it, where I have this neuron S11, and I'm talking about things before the activation. So I know that S11 is equal to this quantity, right? So all the incoming weights to the first neuron, which is W1I into Xi, okay? Now for some reason, I am not telling you why, I am interested in the variance of this. Can you tell me why I'm interested in the variance? What did you see in the previous examples? There was no variance, right? There was hardly any variance. So let's see what happens if we compute the variance of this. So I'm just taking the variance formula. Variance of a sum is equal to the sum of the variances, right? This is of the form variance of A into B, where A is W1I and B is Xi. What's the formula for this? All of you know it or don't know it, don't care. Okay, so this is the formula. Okay, so this is the generic formula for variance of A into B, where you have to assume that A is W1I and B is Xi. So this is just a formula, right? There's no trick here, no math, nothing fancy here. Just apply the formula for variance of AB and substitute A is equal to W1I and B is equal to Xi. Okay. Now I'll assume that all my inputs are zero mean. Fine, we have been assuming that forever. And all my weights are also from zero mean. Okay. What is the effect of that? Which quantities will disappear? This will disappear because mean is 0 means the expected value of the weight is 0. So the square of that is 0. And expected value of the input is 0. So square of that is 0. Okay. So what am I left with? Summation variance of Xi into variance of W1I. Okay. Now I'm going to assume that the variance of Xi is equal to the variance of X. That means it's the same for all the i's. So I had this, remember I had these 500 inputs. So I'm assuming that for all the inputs, the variance is the same. They all come from a similar variance distribution. Okay. And I am also going to make the same assumption for the weights. Fine. And then I end up with this neat formula that the variance of S11 is equal to n times the variance of W into variance of X, right? Because I have assumed that all these terms are equal and there are n such terms. Everyone is fine with the math so far? With the assumptions that we have? Okay. So in general, for any of these neurons, right, instead of just S11, I could take any S1I, and this is what the variance is going to be, variance would turn out to be, because I have assumed that all the weights and all the inputs come out from the same variance distribution, okay, from a distribution having the same variance, okay. Now what would happen if this quantity is very, very greater than 1? The variance of S1I would be very large, right? Okay. And what would happen if this variance tends to 0? Variance would be very low. So I'm just giving you two extremes to build the intuition, and let's see what we are going to do with that intuition. Fine. Now let me add one more layer and see. So I've added one more layer, and using the same procedure as above, we'll arrive at variance of S21 is actually given by this formula. And actually what has happened here is that this I had Xi earlier, but now instead of Xi, I have S1I, because those are the inputs to this layer, right? So this is exactly the formula that we had arrived at earlier, assuming zero mean and the same variance for all the weights and the inputs. And I'm just arriving at the same formula for the next layer, where instead of Xi's, I have S1I's. Everyone is fine with this? Okay, how many of you get this? Okay, fine. So this will result in this quantity, okay? But I already had a formula for variance of S1I. What was that? N into this quantity. So I'll just substitute it there. So I can say that variance of S21 is actually equal to this. I've just substituted this value. Okay? So that turns out to be, I have a square here when I have 2 here. So you see where I'm headed with this? What will be the variance of Ski? This raised to k and to something. Everyone gets this? Okay, I can just continue the same analysis, and I've assumed that these weights and all layers have the same variance, right? So in general, I can say this. Okay. Now can you tell me something about when would this variance vanish? When n variance of W is less than 1. Okay, and which is the thing that we should aim for? We would want this quantity to be equal to 1, in which case it will neither blow up nor shrink. Okay, fine. So to ensure that the variance in the output of any layer does not blow up or shrink, we should ensure that n into variance of W is equal to 1, right? So what is this? Let's take a minute to understand this. I am saying that I'm going to initialize my weights. So I should initialize them in such a way that the weights are coming from some distribution, right? We saw that the distribution was this uniform distribution from where I was drawing the weights. So they're coming from some distribution. I should try to draw them from a distribution such that this condition holds. If this condition holds, then across layers, my activations will not blow up or shrink, because that is exactly what was happening in the earlier case when I was doing those bad initializations with small values and large values. All of you get the idea? Okay, how many of you get this, whatever I just said? Okay, good. So let's see how to do that. So what I'm going to do is, I'm going to consider a random variable z, okay, where z comes from a normal distribution, okay, and I'm going to scale its value. I will draw from there, and then I'm going to scale it by 1 by square root of n. What is n? Number of neurons in each layer, right? Here it's the same across all layers, but it could also be different. So I'm considering a particular layer, and n is the number of neurons in that layer. And now, if w is actually equal to z by square root of n, then I can write that n into variance of w is actually equal to this quantity. Everyone is fine with this? There's no trickery here. I'm just saying that why I'm doing this is not clear. That will become clear, but at least what I'm doing is clear. I'm drawing the weights, I'm taking a random variable z which comes from a normal distribution, and then I'm setting my weights to whatever values I've drawn. I just divide them by the square root of n. Okay? Now let's see, what's variance of az? A square into variance of z. Right? That's a basic formula, all of us know this. Okay? So now what's variance of z by 1 in z into 1 by square root of n? 1 by n into variance of z. Right? So the n and n cancel. And what is variance of z? What did I assume about z? It came from a normal distribution, 0 mean and unit variance. So variance of z is 1. That means this quantity n variance of w is going to be 1 if I have initialized my weights such that they are equal to this. Right? And now do you see whether the weights are very small, very large, or what are they? So I'm now made the weights dependent on the number of neurons. So if you have very large number of neurons, you're drawing weights such that, or you're initializing weights such that it's some normal variable divided by the square root of n. Right? So now when you do this summation wi xi, your summation cannot blow up because you have already divided it by n. How many of you get this? So this is a standard way used for initializing weights. How many of you tried this for your backpropagation assignment? Why did you try this? Huh? Okay, because you are having some problems with saturation, I guess, right? So this is how you should initialize your weights. This is more or less the standard technique and some variants of this, right? Because instead of n, you would have this fan in and fan out, right? How many weights are coming in and how many weights are going out. So you make it proportional to the square root of n into k or something like that, right? So, but in general, this idea, right? Of course, this proof, we arrived at it with a lot of assumptions, but we at least got to some principal way of initializing weights, and this is a largely used standard, this and some variants of it, right? So now let's see if I actually take the same network, that means 5 layers, 500 neurons at every layer, and then initialize it using this. So this is exactly what I had told you, right? That take it from a unit distribution, a normal distribution, and then divide it by the square root of the number of neurons in that layer. And now let's see what happens across the 5 layers. You see what happens? We get this good variance in the activation functions. They are not all going to 0 or 1 or 0.5, right? So this solves the purpose for tan H activation and also for the sigmoid activations, right? You see a good spread in the weights. And remember, actually for sigmoid, although these values look close to each other, but this is the 0 to 1 range. This is actually -1 to 0, which will not happen for sigmoid. So within the 0 to 1 range, you get a good spread if you initialize the weights this way. But it turns out that this initialization does not work for the ReLU function. In the ReLU function, you still see this effect that you started off with a good spread, but as you keep going across depths, this spread disappears. Why would that happen? So someone gave an intuition for this, and it's again one of those heuristic things that in the case of ReLU, you need to account for this divide by half, because half of the ReLU is not active, right? Half of the ReLU is 0. So you need to account for that fact, and do this simple trick that instead of taking the square root of the fan in, you take the square root of fan in by 2. Because you know that half the times it's not going to produce any output, right? So that's a very simple heuristic that someone tried, and that leads to better activation functions, better activations across all these layers, right? So as you see, across all the layers, the spread is good now. So the same idea, okay. So now you have a good way of initializing neurons. So this should help you in your future assignments. Okay, fine. So this is what we have learned about how to initialize your weights, and it makes a lot of difference to how your network will behave, right? And that's what I was trying to show that by computing these activations across different layers, and I showed that as you change these initialization strategies, you get better activations, okay?